Today, I will present the proposal and development of an immersive virtual reality teleconference system for designing infrastructures. Today's contents are as follows. The progress of projects consists of both asynchronous and synchronous works. During asynchronous works, the member of a project each work independently. However, during synchronous works, meetings are held and each member's tasks are stipulated, outlining the responsibility of each member to be completed by the next meeting. Because of advancements in information and communication technology, teleconferences that make use of the internet are conducted more frequently in order to reduce traveling time and costs. Traditionally, remote meetings are held using a flat-screen display-based teleconference system. However, with this method, several problems arise. Firstly, the feeling of the participant presence is absent. Secondly, the lack of mutual understanding, especially when design changes are discussed. For instance, when pointing out objects within BIM models. Finally, the editing function in the shared virtual environment is insufficient. Additionally, multiple remote participants are unable to track and understand changes in the BIM model during asynchronous work. In order to solve the aforementioned problems, when comparing civil infrastructure designs, this research developed an immersive virtual reality teleconference system using product models and tracking design change. This research proposes a teleconference system consisting of the immersive VR teleconference system, design change tracking system, and cloud-based 3D editing system. Thereafter, a prototype system was developed. So, immersive VR teleconference, design change tracking, and cloud-based 3D editing have been extensively researched in the past. However, they failed to satisfy the necessary requirements I mentioned. So the proposed system is called Immersive VR Design Teleconference System, IVDTS. Participants of a teleconference situated in various remote locations and using IVDTS are able to share the immersive virtual environment. During meetings, using 3D models, they are able to track design changes and edit 3D models via the internet. As mentioned in the introduction, a project consists of iteration of individual works and meetings. Our proposed system supports meeting as shown in this flowchart. The proposed system consists of immersive VR teleconference, design change tracking, and cloud-based 3D editing system. So when using the proposed system, the position and rotation of users are synchronized, tracked by head-mount displays. The avatars are made in advance. Design changes made among multiple participants have the following features: iteration of the meetings and individual works, identification of 3D models, inheritance of geometry and attributes of 3D models from other 3D models, multiple participants, and identification of order in which models are edited. Based on these features of design change in 3D models are defined as follows. M is a 3D model, S sub I is a session number, M sub J is a model number, M sub K is a parent of M sub J. P of list of M sub K is a list of parent model numbers. A sub N is a code of engineers who edit the model. T sub Rj is time when the editing of the model is completed. So this slide shows an example of design change tracking model, which we developed. Users A sub B, A sub 1, A sub 2, and A sub 3 changed 3D models. The 3D models changed by users have the information about inheritance defined as this equation. The proposed system uses not only geometry, but also attributes. Operations on 3D models with attributes are as shown in this diagram. We divided operations into two sub-operations. The first operation is operation on geometry. The second operation is the operation on attributes. The operation on geometry is divided into 4 operations: add, remove, change, and move. Whereas the operation on attributes are divided into 3 operations: add, remove, and change. We developed the prototype system for IVDTS. This table shows the software and hardware used to develop the prototype system. In order to construct the immersive VR environment, we use the game engine as our development infrastructure and head-mount display. Moreover, we use the platform as a service for networking and voice chat to develop the shared immersive virtual environment. This figure shows the view of our participants using a developed system. Within the shared immersive virtual environment, users have meetings. In order to use BIM models in the shared virtual environment, we developed a plugin to extract attributes from BIM models. This slide shows the panel with a diagram of design change tracking. The developed system automatically reads the CSV files with the information of design changes. In traditional flat-screen-based teleconference system, the shared environment is displayed on a flat-screen display. The presence of users in the conventional system is far from that of real meetings, in which participants share the same room. The developed prototype system would enable participants to share a virtual environment. Therefore, the feel of other participants' presence would be improved. However, the proposed VR teleconference system lacks the ability to show users facial expression or gestures, apart from the position and rotation of their heads tracked by head-mount displays. The proposed systems' inability to display these facial expression is problematic. Another problem with flat-screen-based teleconference is a lack of mutual understanding of the 3D models. However, when participants use the proposed system, they are able to view 3D models stereoscopically with head-mount displays. Subsequently, participants will have a mutual understanding of the model's 3-dimensional shape during the teleconference. The difficulty in tracking and understanding design change is in the 3D models by multiple remote participants is another problem face during teleconferences. The developed prototype is able to track design changes by dealing with the history of design changes, and users were able to view the track design change during the teleconference. The developed design change system, developed design change tracking system shows differences between design alternatives. Therefore, the proposed system is effective in tracking and understanding design changes. A downfall of the design change tracking system is that it cannot register the data of design changes. The registering system functionality to avoid conflict during moderating needs further development to make the progress of project more effective. In conclusion, we propose a VR teleconference system called IVDTS to support the comparison of civil infrastructure designs. IVDTS consists of the following three subsystems: the immersive VR teleconference system, the design tracking system, and the cloud-based 3D moderating system. Finally, we implemented the proposed system as a prototype system for Bridge. Further development is needed on how users are represented in the virtual environment in terms of facial expression and their gestures. Parametric modeling and quantitative evaluation is required. Thank you for your kind attention.
All right, thank you, and thanks to everybody for keeping so well.